Hey everybody, this is Mr. Neuberts Amazing Video Lesson, and today we're going to do a review of free body diagrams. We've got a different locale. We're in the living room, the kids are gaming down the basement, it's in the playroom, so I'm up here. So free body diagrams, I'm going to go through some examples, a lot of examples of free body diagrams, and then go through that interactive again. If you're having some issues with that, you can get your 12 stars or 6 stars, whatever you're required to do. And here we go. So there's a free body diagram again. It shows whatever this represents, whatever object it is. Could be a car, could be a book, could be a sled, could be a person pulling a sled or something. And it shows the different forces involved. Okay, in this case, you've got frictional force pushing against the object. You've got an applied force, F pulling, let's say, pulling a sled, let's just say, and you got friction between the snow and the sled going the other way. And of course, you're always going to have gravity pulling down on the object. And since it's on the ground, we're saying this is a sled, it's a normal force pushing up. Okay, so let's run through the types of forces involved in these things. You have, again, frictional force. Hope you guys can see that okay. Got a little bit of a reflection on the screen, but the magic screen is not working so well here, but we can get through this. Frictional force. Frictional force between the ground, which is F fric, and whatever direction that is going, it's against the motion, right? Between the wheels and the ground, between the book and the table, whatever is being pushed or pulled. Tensional force, F10s, is force transmitted by usually a rope or a spring, something hanging from a rope, hanging from a cable like an elevator, as I mentioned in the last video. The normal force is always pushing up on an object. Could be a table pushing up on a book, could be a road pushing up on a car, could be the snow and ground pushing up on a sled, something like that. Okay. The other types of forces, we've got F air resistance. Typically they'll use this when something is falling through the air, like a skydiver or a flying squirrel dropping through the air, a bird dropping an egg. The applied force, okay, is a push or a pull in that direction. Okay, could be engine of a car applying force to the wheels. Could be a person pushing a box, pushing a book on a table. Could be an engine driving the wheels in a car, and springs. There's no examples in the interactive, but could be springs or something. And then finally, gravitational force. You're always going to have gravitational force pulling down on the object, okay, unless otherwise specified. So those are your main forces you're looking at. Gravitational force pulling down an object. Applied force, that's a push or pull. The air resistance, usually something falling through the air. The normal force, a table or something pushing up on the ground, pushing up on an object. Tensional force, either a rope, a string, or a cable, so suspending something. And frictional force between the ground and the object. Okay? All right. Here's some examples. And I got to shrink this down a little bit. Get it on the screen. There we go. For number one is a book at rest on a table. Okay, a free body diagram for this situation looks like this. So the box, quiet please, I'm videotaping. The book is on the table. Gravity's pulling down on it. Normal force is pushing up on from the table, pushing up on the book. That's what that free body diagram would look like. And let's move down to the next one. Let's not do that one. I don't like that one. Okay, you've got an egg is free falling from a nest in a tree. So sad. Egg's falling down. Neglect air resistance. So you're going to ignore air resistance. So this one would look like this. A free body diagram for this situation looks like this. So this is the egg that's falling. This represents the egg that's falling. It's a square egg, go figure. Gravity's pulling down. F-grav, the force of gravity pulling down. Normally there would be air resistance pushing up, but it's said to ignore air resistance. Okay? So that's when it's not moving left or right. There's no applied force sideways. It's just falling. That's what that one would look like. Okay. Another example. A squirrel is flying. No wings are flapping from a tree to the ground at constant velocity. It's a flying squirrel, by the way. At a constant velocity. Consider air resistance. Okay, so we got a squirrel, a flying squirrel that's falling through the air. Now we're including air resistance. You got gravity pulling down on the little squirrel and air resistance pushing up against it, like a skydiver, but this happens to be a squirrel. It's a constant velocity. That's what it says. Constant velocity. You got to pay attention to when what information they put in there. Constant velocity, which means he's reached terminal velocity, which you read about yesterday. Okay. Which means his speed is constant. Okay. These two arrows, these two vectors, are going to be equal length. Okay. That's what that one would look like. If he was accelerating, if he just jumped out of the tree and was accelerating, the gravity arrow would be longer than the air resistance. Gravity's winning out. If he's slowing down, if he's decelerating as he's falling, then like when you just pull your parachute for a skydiver, air resistance would have a longer arrow and the air would be winning out over gravity. Still falling, still accelerating, but not by as much. Okay. Next one. A rightward force is applied to a book. Let's shrink this down a little bit. Where'd that one go? All right, here we go. A rightward force is applied to a book in order to move it across the desk with constant velocity. So consider frictional forces, neglect air resistance. It's not falling, doesn't matter. A free body diagram for this situation looks like this. So here's the book. It's moving across the table, okay? But it's at a constant velocity. So obviously you're going to have gravity pulling down the book. The normal force is the table pushing up on the book. You've got frictional force. Let's do applied force first. Applied force, someone is pushing it across to the right. The FAP is applied force to the right. Frictional force between the book and the table is working against it. But since it's a constant velocity, these two arrows are going to be equal. If they're equal, there's no change in the motion. Okay, it could be stopped, it could be moving at a constant speed. That's what those would mean. If he was accelerating with more applied force, this one would be longer than the friction. Okay. Another example. A college student rests a backpack upon his shoulder. The backpack is suspended emotionally by one strap. Okay. A free body diagram for this situation. So it's a strap, and they're using F10s to represent this is the backpack. This represents the strap. Remember, F10s, tensional force could be, a rope, a cable. In this case, a strap from a backpack. Gravity is obviously pulling down on this. Okay, and it's not moving up and down. It's at a constant speed up and down of 0. It's just on the kid's shoulder. All right, got a couple more of these. Skydiver is descending with a constant velocity. Consider air resistance. A free body diagram for this situation looks like this. So this is the person falling, skydiving. Gravity is going to pull down. You've got air resistance working against gravity. And it says constant velocity, so these two arrows are going to be equal. He's still accelerating to the earth, but he's hit terminal velocity, about 120 miles an hour in the case of a skydiver. Okay. When you first jump out of the plane, gravity would have a longer vector than the air resistance because he's accelerating. That's what gravity's winning out if this one was longer. And then at a certain point, about 120 miles an hour for most people, you can't go any faster. You're still going 120 miles an hour, but you cannot accelerate. Air resistance, force of air matches the force of gravity. So you've reached actually terminal velocity, a term we'll talk about on Wednesday. All right. Now I got the kid dragging a sled across this loosely packed snow with a rightward acceleration. Okay, here we go. Here's some acceleration now. So, force is applied. Let me put that on the screen for you. But I want you to see this too. All right. Right, applied force to the right. To drag a sled across loosely packed snow with a rightward acceleration. That's important. Neglect air resistance. Free body diagram for this situation looks like this. So here's the sled. Gravity, you're always going to have F grav pulling down. The ground and the snow create what's called F normal force pushing up on the sled. Okay. Applied force to the right. Okay. F app is applied force. Friction between the snow and the sled is working against the applied force. You know, when you drag a sled across the snow, it's hard because you get some drag. So that's the frictional force working against it. But since it's accelerating, the applied force is beating the frictional force, so it's speeding up to the right. If the kid's walking at a constant speed, pulling this sled, then these two arrows, these two vectors would be the same length. But since it's accelerating, you make this one longer. And a football is moving upwards towards its peak after being booted by the punter. Neglect air resistance. A free body diagram looks like this. Whoops, one bit too big. So it's just looking at just the up and down. I know the punt goes downfield, so I said the other day in this video. And it says to neglect air resistance. Remember, air resistance is working against the ball going upward. So it's just gravity pulling down on the ball. That's what that would look like. The free body diagram. We just got a couple more of these. A car is coasting to the right, so there's no applied force. It's coasting. They ran out of gas. Coasting to the right and slowing down. What's slowing it down? What slows that car down when you run out of gas? Friction between the tires and the road. Neglect air resistance, okay? Free body diagram for this situation looks like this. So you got the car, kind of square, kind of boxy looking car. F grav is always pulling down. Gravity is always pulling down. Force of the normal force always pushing up from the ground, pushing up. And there's no applied force because it's coasting. But you do have frictional force between the tires and the road, slowing it down. Okay? And that was it. I thought we had 12, just 11. All right, let's take a look at this. That interactive. If you're struggling with it, you have a chance to do it till you get enough stars that you're required to do. Open it up. Let's go through this again. I'll show you how to do this, and then I'll cut you loose. Click on a situation. Some of these are going to be the same situations that we just reviewed, actually. A softball player. You can't read that one. There we go. A softball player does a head-first dive and is sliding to the right across the infield. Ignore air resistance. So the first thing you want to do is hit the down arrow. That's going to give you choices. What's pulling down on the softball player? Gravity. There's your F grav. And if you want to increase or decrease these vectors, you just click on it like that. It's going up and down. More gravity, less gravity. All right. Up. If you have gravity pulling down, what's pushing up on the softball player? Which one of these? Gravity, normal force, frictional force, tensional force, spring, air resistance, applied force. Normal force is pushing up. Normal force and gravity oppose each other. Okay? These arrows are going to be the same length. And then they're moving ahead, head first dive to the right. Is there an applied force since she's sliding? There shouldn't be, because once you push off and are sliding, just like the sled, you should not have an applied force. So let's look at the left force to the other direction. You're sliding in the dirt. There's your friction between your body and the dirt sliding. If this program is reading it the way I'm reading it, that there should be no applied force to the right because you're just sliding like a sled on the snow. Let's see if that's how they have it. Yay, that's how they do have it. Okay. Sometimes with these computer programs, you never know what you're going to get. Sometimes they're wrong. Sometimes they interpret things differently. So you got normal force pushing up, gravity pulling down, frictional slowing down the player. They're sliding, okay, along the ground. They're not pushing off, okay. If they applied a force when they first started running, then yeah, you'd have an applied force and friction between the shoe and the dirt, okay. So there's a quick review. You could go back through if you haven't done the free body diagrams. Do those. Do your free body diagrams. Get your work in. Hopefully you worked on that yesterday. Got a lot of the stuff cleaned up that is due. The brain pops. There is a forces brain pop and a gravity brain pop. Those both need to be completed and sent in. Quick note on the Olympics friction. It's pretty clear that it's the Olympic friction, and there's a big Olympic rings, and the directions include a website to go to for Olympic sports. Walking up a stairway, carrying a book bag, breathing is not an Olympic sport. Guys, use the list to get the right sport. If you need to go back in and change some things because you missed those instructions, do so. Clean those up. They're Olympic sports, winter or summer, that need to be in there. And I think that's it. Have a good Cinco de Mayo today. And adios, muchachos. Hasta la vista.